I want you to take a second and just look around your environment.
Really take it in.
Yeah, exactly. Just notice the colors of the objects around you, maybe the depth of the room,
Yeah.
the really sharp details of whatever's sitting right in front of you.
It feels completely immediate.
Right, it feels incredibly real. But here's the bombshell. Absolutely none of that is actually entering your eyes.
None of it at all.
Literally none of it. What you're experiencing right now is this, like, incredibly convincing virtual reality. And it's being generated entirely in the pitch black of your skull.
Which is just a wild concept to wrap your head around.
It really is. And that is the core premise of this fascinating piece of neuroscience we're unpacking today. So welcome to today's deep dive. We are looking at a document by Dick Kukin, and it's titled Zien Wat is Dat, which translates to Seeing What Is It?
And it's just brilliant.
It is. The mission for our deep dive today is to completely deconstruct this illusion of human vision. We're going to explore how our brains, compress, hallucinate, and project the reality that you and I experience every single second of the day.
And just to set the baseline for this conversation right up front, we really have to leave philosophy at the door here.
Oh, absolutely.
We are looking at hard neuroscience today. So every single thing you think you're looking at, from, the light waves bouncing off a coffee mug on your desk to the vivid blue of the sky, it's nothing more than a translation of biological data.
Just pure data.
Exactly. And our goal today is to trace that data's journey, really step by microscopic step, from the chaotic outside world right into the dark, silent projection room of the mind.
Okay, so let's unpack this. To understand how the brain fabricates this, beautiful, seamless image we think we're seeing, we first have to understand the biological hardware.
Right, the eyes.
Yeah, specifically just how terrible our eyes actually are at capturing raw data. Because the physical world is, it's pure chaos.
Oh, it's a mess out there.
Right. You have electromagnetic waves traveling at 300,000 kilometers per second, and they are just slanging at the front of your face.
And the sheer volume of that light, it presents this massive mechanical problem for the body.
How so?
Well, when those waves enter the eye, they hit the retina at the back, which is essentially this biological capture screen lined with receptors.
Yeah.
You have about 100 million rods, and those are dedicated strictly to measuring light intensity, so just light and dark.
100 million, wow.
Yeah, and then you have about 7 million cones, which are the ones sensitive to specific wavelengths of light. Color, basically.
And if I remember the source correctly, almost all of those color-sensitive cones are packed into this ridiculously tiny spot.
Right, the fovea.
Yeah, it's like a 1.5 millimeter spot in the dead center of your retina.
Which creates a fundamental bottleneck in human vision. Because think about the math here. You have roughly 107 million of these receptors picking up data every fraction of a second. But they have to send that massive amount of data to the brain through the optic nerve.
And the optic nerve is not very big.
It's remarkably narrow. It only contains about 1.2 million axons, or nerve fibers.
So, okay, it's like trying to download a 4K movie through a 1990s dial-up modem.
That is the perfect analogy. You literally cannot fit the data through the pipe.
So if you have 107 million receptors trying to shove information into a cable that only holds 1.2 million fibers, that means like 99% of the pixels are being dropped before they even leave the eye.
Exactly. They just vanished.
Then how are we not just stumbling around in a total blur?
Well, the secret lies in what the retina is actually doing. You see, in neuroscience, the retina isn't viewed as a passive camera sensor.
It's doing something active.
Yeah, it's considered an active outpost of the brain itself. It does not send a picture down the optic nerve.
Oh, interesting.
Instead, it aggressively pre-processes the raw data. It takes those 107 million points of meaningless, chaotic light, and it compresses them into highly simplified, primitive outlines.
When you say primitive outlines, what do you mean?
We are talking about microscopic lines, tiny corners, curves, edges. That incredibly basic line art is the only thing that actually fits through the bottleneck of the optic nerve.
Just isolated contour fragments. Nothing else.
Just the bare bones, yeah.
Which completely explains a physical limitation that you can actually test on yourself right now.
Oh, the thumbnail trick.
Yeah. So if you hold your thumb out at arm's length, the only place you can actually read text or see any sharp, high-resolution detail is in a tiny 2 to 3 degree window of your vision.
Which is basically the exact size of your thumbnail.
Right. Everything in your periphery outside of that tiny spotlight is just blurry shapes and movement. Your eyes are capturing almost no useful detail out there.
which completely shatters the illusion that our eyes are like these high-end video cameras, right?
It really does.
I mean, if our conscious experience relied purely on the raw data squeezing through the optic nerve, our vision would be this jagged, chaotic mess of moving outlines.
Just a blur with a tiny pinhole of clarity in the middle.
Exactly. But obviously, you and I, we experience a full, rich, wide-angle, seamless world.
So that's the big question, right?
Yeah.
How does the brain take a few jagged little lines and a blurry background and turn it into the 4K IMAX movie I'm experiencing right now?
It does it by relying on a mechanism called top-down memory projection.
Top-down memory projection. Okay.
Yeah. So those compressed signals, the lines and corners, they travel from the optic nerve all the way to the back of the brain, hitting the occipital lobe.
Right.
And they land in an area called V1, the primary visual cortex. It's surprisingly small, actually.
How small?
About the size of a standard credit card. And it contains maybe 200 to 300 million neurons.
Okay, and here's where it gets really interesting in the document. When those primitive lines and corners finally hit V1, they don't just, sit there waiting to be looked at by the brain.
No, not at all. They act as a trigger.
Right.
They act as a trigger for your memory catalog. So those incoming outlines automatically and instantaneously activate thousands of existing visual memories in parallel.
That's crazy fast.
It is. The data then moves to adjacent areas, V2 and V3, which try to group those fragmented lines into coherent shapes.
Oh, they're looking for patterns.
Exactly. If those shapes match a biological pattern you've seen before, say, the curvature of a coffee mug handle or the specific geometry of a letter of the alphabet, your brain instantly pulls up the full, rich, high-definition memory of that object.
And then those active memories loop backward. They feed back into the primary visual cortex.
Right. This is the critical mechanism of top-down feedback. The brain is literally projecting the stored memory onto the visual cortex.
It's painting over the crude outlines.
Yes, painting over them with high-resolution detail from your past. And this continuous loop, raw outlines triggering a memory, and the memory projecting back, it happens incredibly fast.
Okay, how fast are we talking?
If you are just sitting still and reading a book, this feedback loop fires 10 to 30 times a second.
Wow.
And if you're tracking something fast and unpredictable, like a tennis ball during a match, that loop can run 30 to 100 times a second.
Okay, wait, I need to stop you there because, honestly, the logic of this feels like a paradox to me.
How so?
Well, if I am just projecting my own memories onto crude outlines, how do I ever see something I have never seen before?
Ah, right.
Because if a friend hands me a brand new, bizarre-looking piece of technology, I don't go blind. I can see it perfectly.
Right, you still see it.
So how does that work if I don't have a pre-existing memory of that specific object to project?
That is the beauty of how the visual cortex breaks down information. You see, you don't need a memory of the specific object as a whole.
Okay.
You have a massive library of fundamental building blocks. You have memories of metallic textures, memories of a right angle, memories of the color silver.
Oh, I see. Memories of how light reflects off a curved surface.
Exactly. So when you're presented with a novel object, your brain rapidly triggers thousands of these micro-memories and stitches them together in real time to build a composite projection.
So you are still projecting memories.
Yes, you're just remixing them to fit the new geometry the retina is sending.
So even when it's totally new, I'm still just watching a collage of my own past experiences.
You are. And science offers undeniable proof of this through transcranial magnetic stimulation, or TMS experiments.
Okay, what do they do in those?
Well, researchers can use a targeted magnetic pulse to temporarily disrupt highly specific neural pathways in a conscious person.
Just zap the brain a little bit.
Basically, yeah. And if they use TMS to block that top-down memory feedback loop from returning to V1...
While the person is awake.
While they are wide awake, leaving their eyes wide open, the optic nerve firing, and the raw data pouring in.
What happens?
The subject goes completely functionally blind.
Just from blocking the memory loop.
Yes. The raw data from the outside world is hitting their brain. But without the memory projection to give it form, texture, and meaning, the brain cannot process it. The raw data is absolutely useless on its own.
That is wild. So if our vision is essentially a memory projection, a very convincing story the brain is telling itself 30 times a second.
Yeah.
there have to be scenes in the simulation, right? Like there must be glitches where the brain has to actively scramble to cover up its own biological flaws to keep the illusion from breaking.
Oh, absolutely. In fact, you carry one of the most glaring glitches with you everywhere you go.
The blind spot.
The blind spot, where that 1.2 million fiber optic nerve physically leaves the back of the eyeball. There is a literal hole in the retina.
There are 0 light receptors there, nothing.
It's a total dead zone. Yet, as you look around the room right now, you don't see 2 black holes floating in your field of vision.
Right. And the reason is that your active memory is continuously projecting a seamless image over that gap.
Exactly. Since the brain never receives any conflicting data from that specific spot because there's no hardware to send it, it just fills it in with the surrounding pattern from its memory catalog.
It's like it behaves like the content-aware fill tool in Photoshop.
It is exactly like that. It's literally painting over the hole in your biology.
And it paints over motion blur too, doesn't it?
Oh, yeah. Saccades.
Right. We have these rapid eye movements called saccades. When you shift your focus from one object to another, your eye moves so incredibly fast that any raw visual input would just be this nauseating smear of color.
So the brain actively suppresses the visual input during that jump.
But we never notice the blackout.
Wow.
Our vision feels perfectly smooth.
It's amazing.
I actually read about a trick you can do to prove this. If you go to a mirror right now and look closely at your left eye, and then suddenly shift your focus to look at your right eye, you will never see your own eyes move.
No.
A friend standing next to you will see them dart back and forth, but you won't. Your brain edits the movement out of your conscious experience entirely to maintain the illusion of a stable reality.
Which points to a fundamental rule of how our nervous system operates. Specifically, a concept known as synaptic tuning.
Synaptic tuning.
Yeah. The brain is incredibly efficient, and it absolutely despises wasting energy on redundant information.
Right, which perfectly explains the microsaccade laser experiment from the source material.
Oh, that is a great one.
Honestly, this was one of the most mind-blowing things in Koiken's notes. Even when you think you are staring perfectly still at a fixed point, maybe looking at a star in the night sky, your eye is actually vibrating.
Those are the microsaccades.
Right, these tiny involuntary twitches happening 1 to 3 times every single second.
They are microscopic, but they are biologically vital.
So, researchers wanted to know why we have them. They set up this experiment using lasers and specialized monitors to track a person's eye with pinpoint precision.
Really tracking every microscopic jitter.
Right. They took an image on a screen and stabilized it perfectly so that every time the person's eye had one of those tiny twitches, the image on the screen moved exactly with the eye.
So they mathematically neutralized the microsaccade.
Exactly. And the result was terrifying. The subject went functionally blind in 3 to 5 seconds.
Just gone.
Yeah, the image just dissolved into gray and completely vanished.
And that is synaptic tuning in action. You see, when a neural signal doesn't change, when it remains perfectly static, the brain's synapses perfectly tune to it.
Meaning what, exactly?
Well, the amount of neurotransmitters being released matches the receptors exactly, and the synapse effectively stops firing new information. It decides the signal is no longer relevant and stops registering it consciously.
So the brain basically gets bored and hits the delete key.
Without constant change, yes. If the visual input is absolutely static, it disappears from consciousness.
Wow.
We biologically require those constant tiny eye twitches, those microsaccades, to disrupt the signal just enough.
So by constantly shifting the data by a fraction of a millimeter, the synapses are forced to keep firing.
Right, which keeps the image in our conscious awareness. Your reality has to be continuously refreshed and rewritten by physical vibrations just to prevent the absolute stillness of the world from rendering you blind.
Okay, so if my brain is constantly projecting this movie and aggressively erasing static signals to save energy, what happens when the projection engine is overwhelmed with too much input?
Like in a busy environment.
Yeah, like when I'm standing in a crowded, noisy bar, does the system just crash?
It doesn't crash, it shifts strategies. Think about the cocktail party effect.
Okay, yeah.
You're surrounded by dozens of competing conversations, clinking glasses, background music. It's a tidal wave of auditory data. But if someone 20 feet away casually says your name, you hear it instantly and clearly.
Because my brain is filtering out the background noise to find the important signal.
Right. It goes far beyond simple filtering, actually. It is active inhibition.
Inhibition.
Yeah. To focus your attention, your prefrontal cortex deploys inhibitory neurons to actively block and suppress all competing memory signals.
Oh, wow.
Your name has a very low threshold for activation in your memory network. So focusing your attention isn't just about turning up the volume on the thing you want to hear.
It's about aggressively muting everything else.
Yes, paralyzing millions of other neural pathways in your brain so that one single dominant memory can surface.
That makes a lot of sense.
Yeah.
So then what happens when you cut the sensory input off entirely? Like when you go to sleep and close your eyes, the outside data stops, but the projection system just keeps running on its own.
Ah, dreams. During non-REM sleep, your brain physically alters itself. There was a fascinating mechanical process discovered back in 2012 involving the glymphatic system.
Right.
Think of non-REM sleep like closing down a busy restaurant for the night to deep clean the kitchen. The brain cells actually shrink physically.
They shrink.
Yeah, shrink. This allows a clear fluid, the glymphatic system, to rush in and wash away toxic waste proteins that have built up during the day.
Well, you can't serve food while power washing the kitchen floor.
Precisely the concept. To protect the integrity of your delicate memory structures during this chaotic cellular washing process, the brain isolates its different modules.
So the visual cortex gets cut off.
It's cut off from the rest of the sensory network. But without the heavy anchor of raw sensory input from the eyes to keep it in check, your visual memory system just starts freewheeling.
It just runs wild.
It is free to project entirely internal worlds. You experience full environments, complex emotional situations, and the vivid, blinding illusion of light entirely in the pitch black of your skull.
And that is what a dream is.
That's what a dream is.
Which perfectly explains why hallucinations happen when the hardware breaks down while we're awake. The Kuchen document brings up Charles Bonnet syndrome.
Yes, a perfect example.
This occurs in people who are visually impaired, maybe suffering from macular degeneration or losing their sight to age. And because the physical hardware of the eye is failing, the brain isn't receiving a strong, consistent sensory signal. But their visual memory network is still perfectly healthy and intact.
And as they say, the brain abhors a vacuum.
Right. So the memory projection engine essentially overpowers the weak sensory input from the failing eyes, and the person starts actively hallucinating.
It's very common.
Yeah, they might see vivid geometric patterns on the walls, or animals sitting on their furniture, or even detailed figures of people walking up and down their stairs.
It's wild to experience.
But it isn't a psychiatric issue at all. It is a mechanical one. It's their brain desperately trying to project a reality without enough raw data to anchor it.
Which really brings us to the most profound realization in all of neuroscience. And this touches on the nature of experience itself. Think about color.
Okay.
The physical universe does not possess color. A tomato sitting on your counter is not actually red.
Wait, a tomato isn't red. Okay, you have to break that down for the listener.
A tomato is composed of molecules that simply reflect a specific wavelength of electromagnetic radiation.
Right, just a wavelength.
Your eye happens to have a type of cone receptor that is sensitive to that specific wavelength. But the experience of the color red, the vividness, the warmth, the undeniable redness of it,
Yeah.
that is a purely subjective memory construction generated in the brain. It's what philosophers and neuroscientists refer to as qualia.
Qualia, the subjective felt experience of a thing.
Exactly. The philosopher David Chalmers famously called this the hard problem of consciousness.
Why is it the hard problem?
Because science can track the electromagnetic wavelength hitting the retina. We can measure the electrical signal traveling down the optic nerve. We can even watch the specific neurons fire in the V4 color processing center of the brain.
Okay, we can map all the plumbing.
Yes. But how does that cold biological electrical firing suddenly translate into the rich, subjective, emotional experience of the color red? We know that our visual memories of surfaces are built from these specific receptor activations. But the actual transition from a data point to a lived, felt color remains one of the greatest mysteries in human science.
So if color is entirely a construction, and the objects I'm looking at are just rapid memory matches being projected backward into my visual cortex, why do I feel like I'm inside a room? Why do I have this unbreakable, visceral illusion of physical, three-dimensional space extending away from my body?
Oh, that's fascinating, because three-dimensional space is an active calculation, not a passive observation.
An active calculation.
Think about it. The signal coming from each of your retinas is fundamentally two-dimensional. It's entirely flat, like a photograph.
Right.
But because your eyes are positioned a few centimeters apart on your face, they capture the world from slightly different angles.
So we have two slightly different flat pictures.
Right. And when those two flat, slightly offset signals meet in the primary visual cortex, the brain compares the minute differences in the angles, that's binocular disparity, and mathematically calculates depth.
But why go through the immense computational effort to generate a 3D environment? I mean, if I already know what the objects are from my memory, why do I need the space between them?
Because object memories are isolated files. Your memory of a pedestrian and your memory of a crosswalk are stored as separate, distinct concepts in the brain.
Okay.
So in order for you to understand the relationship between them, to know if the pedestrian is on the crosswalk, near it, or standing behind it, the brain has to simulate an environment.
Oh, I see.
It has to project those isolated memory files into a constructed 3D space to establish physical context. The space you see around you, the distance between your chair and the wall, it's essentially the brain's way of mapping how its own memories relate to each other in real time.
So space is just the desktop where your brain arranges its files.
That is a great way to put it.
We are generating the feeling of space itself just to keep our memory files organized. That is staggering.
It really is.
I want to take all of this, the synaptic tuning, the color construction, the exhaustion of neurons, and give the listener something totally practical. There was an experiment mentioned in Creakin's notes that blew my mind, something called the lilac chaser.
Oh, yes.
I actually pulled it up on my phone earlier and tried it.
It is the perfect scientific hammer to drive home everything we've discussed today.
So if you have a moment later, search for Jeremy Hinton's 2005 lilac chaser illusion. I'll paint the picture for you so you can visualize it. You're looking at a screen, and in the dead center is a small black cross.
Okay.
Arranged in a circle around that cross are about a dozen fuzzy purple dots. Now, one by one, a single purple dot disappears and reappears, moving around the circle clockwise, like a gap ticking around a clock face.
Right.
The instructions are incredibly simple. You stare intensely at the black cross in the center. Do not move your eyes.
So you're forcefully suppressing the microsaccades.
Right. And as you stare, keeping your eyes perfectly still, something impossible happens. The blank spot that is moving around the circle suddenly turns bright, radioactive green.
It's crazy.
You are staring at a computer screen that only contains purple dots in white space, but you clearly, undeniably, see a vibrant green dot running in circles.
And it gets better.
It does. If you keep staring, fighting the urge to move your eyes, all the purple dots disappear entirely. You are left staring at a blank white screen with a single green dot running around across.
Let's break down the mechanics of exactly how your brain is lying to you in that moment. First, consider the color purple. Purple light doesn't exist as a single wavelength. It is a combination of red and blue light.
Right.
As you force your eyes to remain perfectly still, staring at the cross, the synapses in your brain that are registering the red and blue light from those purple dots become perfectly tuned.
The signal is static.
The signal is static, so the synapses run out of neurotransmitters or simply stop firing. They become exhausted.
So they tune out the purple completely.
Now, look at what happens in the blank spot. The blank space between the dots is white on your screen. And white light is a combination of all primary colors: red, blue, and green light.
Okay.
When the blank space moves over a spot where a purple dot just was, your eye receives the full spectrum of red, blue, and green light. But your red and blue synapses in that specific spot are completely exhausted.
Oh, they have tuned out and cannot fire.
Exactly. So your brain only has the capacity to register the green light.
It calculates the white light minus the exhausted red and blue, leaving only green.
And eventually, because you are holding your eyes perfectly still and overriding your natural eye twitches, the synaptic tuning completes for the entire circle.
Right.
The brain decides the static purple dots are no longer new or relevant information, deletes them from your consciousness to save energy, and you are left hallucinating a green dot on a blank screen.
It proves that we don't look at the world, we project onto it. We are literally overriding the physical reality of a glowing computer monitor based purely on the chemical exhaustion of our own internal synapses.
It forces you to accept that what you consider to be objective reality is really just the brain's best, most energy-efficient guess, continuously updated by tiny twitches of the eye.
As Dick Kukin beautifully puts it in the source material, we are nothing more than a room full of blind cells, dreaming a meaningful reality together.
It's poetic.
The brain has never seen the sun. It has never seen a tree. It sits in total darkness, translating electrical pulses into the vibrant 3D world you are sitting in right now.
You are not a passive observer of the universe. You are the active architect of your own visual reality.
Which leaves us with one final, lingering question to wrap up this deep dive.
Okay.
According to the research, it takes human babies about 6 months to develop the visual memory structures required to actually see a coherent external world.
Right, they have to learn to see.
For those first few months, a newborn's eyes are functioning perfectly. They're receiving the full 4K data stream of light. But they don't have the memories to project back onto it, so they just experience a chaotic, meaningless mess of primitive contours and light intensity.
They have to build the catalog of memories before they can project the movie.
Exactly. The data is there, but the world is invisible to them because they lack the memory to decode it. So here's something for you to mull over as you go about your day.
What's that?
If we can only consciously see what we already have a memory for, what else is out there?
That's a great question.
What entirely real physical phenomena are sitting right in front of you at this exact moment? Things interacting with your environment, reflecting wavelengths into your eyes that you are physically incapable of seeing simply because you haven't built the memory structures to project them yet. What are you blind to right now? Thank you for joining us on this deep dive. Keep questioning what you see, and we'll catch you next time.